So here's another really brilliant statement. 66 to 75% of soil nitrogen is not in the humus, but in the microbial proteins. Now, what did he just say? Organic matter. We calculate approximately for every 1%, 20 pounds of nitrogen. But what he's saying is the nitrogen's not in our humus. The nitrogen, the vast majority of it is in the microbial proteins. That means it's in the bodies of the microorganisms. How do we get it out of the microorganisms and into the plant? Another wonderful gentleman, Rudolf Virchow. If I could live my life over again, I would devote it to proving that pathogens seek their natural habitat, diseased tissue, rather than being the cause of the diseased tissue. That is, mosquitoes seek the stagnant water, but do not cause the pool to become stagnant. So we're going to take one more slide. Dr. William Albrecht, professor of soil science, University of Missouri for 4 decades, 40 years. The presence of insects, disease, and pathogens in the field is not the reason for the crop failure. These are merely indicators that the crop has already failed. So this brings us to another brilliant concept that the researchers completely understood. Microbes are present only if there is a correct food source. Pathogens are attracted by a different food source than our beneficials. So in nature, pathogenic microorganisms do not have the capacity to digest nutrient-dense, high mineral, high carbohydrate plant material, and they don't. It's toxic to them. What they can digest is low sugar, low mineral, nutrient deficient plant material. And so when nature calls in the pathogens, whether it's a fungal pathogen, an insect pathogen, a soil-borne worm, it's there because the mineral profile is not adequate in that plant, 1 for food and 2 for reproduction. One rule in nature. Pathogens produce toxins, beneficial microbes produce nutrition. Another brilliant statement. Mineral fertilizers do not diminish, but on the contrary, they noticeably increase the content of inhibitors or pathogens. Mineral fertilizers refer to inorganic chemical fertilizers void of bioactivity. This is our synthetic salt and acid-based NPK products. They increase dramatically soil pathogens. The soil possesses the ability to rid itself of pathogenic bacteria entering it. What this is basically saying is soils have the process. They contain the intelligence of self-purification. Good guys can control bad guys. It's how do we alter that environment so that we sponsor the good guys, or are we sponsoring the pathogens? Because if we increase the pathogen content in our soils and we prosper those populations, we're suppressing the beneficials. And we do this with the inputs that we attempt to feed the plant with. And so if we're conscious of what's toxic to microorganisms, we can drive the beneficial colonies to then control the pathogenic colonies and purify these soils. They'll remove the pathogenic and the phytopathogenic microorganisms or antagonists. Microbes on the leaf also play an important role in plant nutrition and protection. So just as we know that a pathogen can come through the air, land on a leaf, produce a toxin and begin to kill it. So, or it can get into a plant internally. We understand that these pathogens can damage plants. Well, why can't we put a beneficial microbe on the plant leaf with nutrition and establish a beneficial colony so that it protects and feeds the plant rather than leaving the plant available to a pathogenic organism? It is well established that plants can absorb various microbial metabolites, vitamins, antibiotics, and other compounds through the leaf surface. These substances not only enter the plant through the leaves, but they can be introduced by this route in large quantities for the purpose of feeding, as well as for fighting bacterial and fungal infections. So here we have an organic product that is made by microorganism fermentation. The name of this product on organic certification is Soluplex. Biorelease is the non-organic or conventional product, but they do the same thing. Just registration names are the difference. And so what we have done all over the country is we have taken soils and we've compared what happens in the soil when we use Soluplex or Biorelease. So the first line is, what is soluble just from water? And this was the Utah State University analytical lab for soils that ran these tests for us. And so you can see boron, calcium, cobalt, copper, iron, potassium across the top. What is water soluble? The next line is with a half of a gallon of this biological nutrient stabilizer, the boron increases from almost 0.6 to almost to 2. With a gallon, it increases to 3. Now you'll notice that these minerals release at a different rate. Some have single charges that are positive, some have double, some have triple, some have 4 positive charges. The ones that are heavily charged, 3 and 4 charges, release less. Ones with single charges, even double charges, release a lot easier. So as you go through here, you'll notice this. And so if you look at iron, okay, with water, it was more soluble. It wasn't soluble, it was less soluble with a half a gallon and a little bit more soluble. Iron has 4 charges. It's not going to release easy. Potassium, a single charge, goes from 5 to 69 to 168 parts per million. That's a big increase. Calcium goes from 6 to 47 to 67. Notice that there's hardly any molybdenum that shows up. So our nitrogen fixing bacteria are a little bit on the short side. Phosphate goes from 0.3 to 4 to almost 10. Sulfur goes from 0.5 to almost 5 to 11. Zinc goes from 0.01 to a half to a little over 1. And you can go down, and we have these in Iowa, we have them in Illinois, we have them in Minnesota, Kansas, Nebraska, Utah, Idaho, Montana. It's all relatively the same. What we're doing here is we're solubilizing in a very biological, non-toxic way, because all Biorelease and Soluplex are doing are substituting positive and negative charges. And it mildly releases those bonds, and then it helps stabilize these nutrients in the soil. And they're there for months, literally months, for the microbes and the plants to use. So those massive sunflowers, how we accomplished that incredible growth was we put down 1 gallon of Soluplex or Biorelease per acre with the seed. There was we stabilized some 1034 with it because we were able to neutralize the 3 negative charges on the phosphate. Those fields had virtually no phosphate in them, any soluble phosphate whatsoever. And so we needed to add a little bit of phosphate. So we stabilized the phosphate so we wouldn't lose it. And the Biorelease solubilized the entire mineral profile. So we had this massive microorganism growth because those microorganisms had all the minerals to reproduce cells. So the more microbes down there breathing in oxygen, exhaling carbon dioxide, became a huge contributor to the plant. As the plant also had soluble minerals in its root system because of the biorelease, it was able to assimilate cells and cell division much quicker because it wasn't waiting for minerals that were missing and slowing down the process. So this potato plant tells us a very interesting story. So if you know anything about potato plants, this is one plant with 17 uniform tubers or potatoes on it. I'm going to go to the next one real quick. This is the same type of plant 100 feet away in the same field under a different form of nutrition. So this, we'll call it Company X, came into this grower in Idaho and said, we have a better program than what you have. And so they talked him into getting half of the field, and we kept the other half with the program that we had been running. This plant has 6 or 7 tubers of different size. Now in a potato, it will go through sets, and when it has enough mineral and energy, it will set and hold all those tubers. When it is lacking minerals and energy, it will set the tubers and then abort that which it can't hold. And so what this plant is telling us, because we have tubers of all different sizes, this has been through 4 sets of abortion. It threw tubers and then would be able to keep 1 or 2. Then it would reset, and 2 weeks later, it would throw another set of tubers and keep 1 or 2. And the previous plant set and held 17 all at once and maintained them. And so the whole different profile of plant performance is based here on soluble minerals. There was 2 gallons of Soluplex or bioreleased used on our side of the field. The other side of the field used fish, chicken manure, and humic acid, which are not plant soluble. They're not plant available. And so the plant will tell you how it's doing. Every time you set potatoes and lose them, you lose 50 sacks or 5,000 pounds of potato per acre. So that's not a process you want to go through. Seed treatment. Okay. All right, so our seed treatment. This is going to increase germination, seed survivability, reduce disease, increase water efficiency, increase fertilizer efficiency transfer, increase CO2 production, strengthen the plants. Here's some barley seed that was chemically treated. One of our farms in Montana decided to do an experiment. He decided, I'm going to germinate this seed. So he put a wet towel over it. On the left was just the fungicide, insecticide treatment. On the right, he treated it with our seed treatment. And after 72 hours, you can see very little activity on the left, a great deal of sprouting beginning to occur on the right. Another farm was, we had planted winter wheat, and the next spring, the gentleman sent me a picture of the 2 plants, one without it and one with it. And on the side of the barley, we simply had the poison, fungicide, insecticides. With the seed treatment, we had the beneficial microbes, we had the solubilized minerals, we had the growth factors, vitamin enzymes, and the whole process with germination, it's all enzymatic driven. We have to have those trace minerals there to drive this system. And so you look at, this was a seed treatment that we did back in 2013 for Byron Seed in Indiana. And so they took it, and this is what they published from their trials. This is not information that we did. They sent us, we got a copy of this after the fact, but they did 5 fields with and without. And so they split these fields. The results of the seed treatment were the treated side planted at about 33,000 plant population. Field 1, 31,000. Field 2, 30,000 surviving plants. Field 3, 32. Field 4, 33. Field 5, 29. So we averaged 31,000 surviving plants, averaged 254 bushel. On the untreated side, same seed and same fields, we had 22,000 surviving plants, 27, 22, 25, and 23,000. So we averaged 24,000 plants. 7,000 less plants survived per acre. Average yield of 217, difference of 37 bushel. At $4.20 corn, there's a $500 or $157 difference. This product costs about $10. This is corn here in northern Utah. 2 fields, 1 got treated, same farm. They treated 1 field and not another field. We went and took pictures. We brought plants back, and we just looked at the root, the stems, the stalks, the ears, the leaves. We just measured it out. And there's a dramatic difference in what the plants are able to do with the microbes and the minerals on the seed. We had nothing to do with any of the other fertility, simply a seed treatment. This is a $7 an acre seed treatment. This is another farmer that sent us pictures, treated part of the field, didn't treat the other part of the field. Alfalfa, the only farm that I have seen produce more than 10 tons of alfalfa per year was seed treated. It's in Alliance, Nebraska. It's Ted Underwood's farm. This is back in 2014. Wheat heads in Montana. These are 5-inch long wheat heads. They have right at almost 100 kernels. From 2014 to 2015, you can continue to see the improvement. Another Montana colony. This was the same colony that we grew the sunflowers on. We planted winter wheat. I was up there early the next spring. The fields that were untreated were on the left. Our treated plants were on the right. Quite a little bit of a difference, even early on. These are the treated winter wheat heads. These are the untreated NPK fertilizer heads from the other part of the farm. On this colony, we would get half the farm we could do under our biological programs. The other half was under fertilizer program. So at the end of the season, the farm boss simply sent me pictures. Abe showed me the heads from the fertilizer side and heads from our side. So on the sunflower pictures, again, these sunflowers are traditionally what they have grown for 20 years. This is what they look like, 500 to 700 pounds per acre. These are the sunflowers that came in at 2,000 pounds per acre. Same field, same planting date. We just simply altered the biological nutrition and put in seed treat. And so the plant will tell you, it will absolutely express what minerals are available and what growth stimulants are there. So Jamie Dillard sent us this picture. Brix reading of 22.5 from his pink eye peas with an excellent level at 12. His Ford Hook peas in 2019 yielded 203 bushel. where they typically average 60 to 75. Another picture Jamie sent me of his turnip. This is an 8-pound turnip. Well, not quite 8 pounds, but very close. And this is what it looks like in a 5-gallon bucket. Jamie sent me some turnips out that were huge, and they were absolutely delicious. This is wheat here in northern Utah. We have a custom farmer that took 3 farms that he farms from, and he decided, I'll treat part of the field and not treat part of the field. And so I'm not sure what farm W is, but there's W treated, W untreated, B treated, B untreated, M treated, M untreated. And the plants will tell you what it's happening in their root systems and the nutrient availability. We have nothing to do with any fertility in any of these fields. They're not under our management. This is seed treatment only. This is one of my distributors, Len and Wanda Horse, up in Sequim, Washington. Wonderful, wonderful people. They run a stand for small farms and gardeners. This is a tomato plant that someone dropped off because it was not looking good. With their microbial, mineral tea, and compost tea, they brought this guy back to life in a great way. This is Len's cherry tomatoes. No fertilizer whatsoever. This is simply microbes and minerals in a soluble form. This is a strawberry that, and you can see on the sign in the back, mineral tea for plant functions, because there's a lot of minerals in that, compost tea improving soil health. So this is just a strawberry plant that he put out on a 55-gallon drum. Well, the drum wasn't big enough. So the next year, he got a bigger container so he could grow better strawberries. These are pictures of Len's peas with a jug of mineral tea he's about to give them. Here's some onions that my dad grew. He uses no fertilizer whatsoever. This is Ted Underwood's field in Alliance, Nebraska. By putting on the minerals and the microbes just one time, his 3rd crop cutting of alfalfa increased 36%. This plant, it was 36% above his 3rd crop average yields. These plants were up to the rim of the pivot tire, which is over 36 inches tall. There's a picture of his leaves. And so 3rd cutting in 2010 increased 36%. And on dairy quality, it was in excess of 54.4. The 4th cutting increased 45%. The TDN increased as well. By the 4th cutting of 2011, it was up 63%, as well as the quality. And this field, we never got to 10 ton. We got to 9.8 ton. Ted took it out, and it was in 2013, 2014, when it went back in, that we broke 10 ton. So when you look at the plant's nutrient demands, the soil microorganisms activity is going right along with the peak demands. When the plant is demanding that nutrition, the soil microorganism activity needs to be right in parallel with this. It needs to be happening at the same time. Generating greater amounts of CO2 this is the broad spectrum general beneficial microorganisms. We're going to put out a lot of fungi, protozoa, nematode into the soil atmosphere and soil environment to create massive amounts of CO2. And these are the guys that aren't like the seed treatment. The seed treatment are very direct, very specific microbes that are going to do very specific things. And we're going to put out millions and billions of times more microbes through the microbial mineral T. And so in this, we did some analysis. So the humates that we use are loaded with protozoa. And what we wanted to do was see how well our biorelease or our soluplex grew protozoa. Because remember, our protozoa are absolutely critical in the predator-prey relationship to eat bacteria and release that entire string of soluble minerals to the plant. So what we did is we took a control and a treatment. We did a 1 hour, a 2-day, and a 7-day. And we did water in the first control, and we did soluplex in the treatment. So as we started, we had what we were looking for is our protozoa groups, which are flagellates, amoebae, and ciliates. Now, you don't want ciliates in high numbers because they're anaerobes. So you want to keep this aerobic. And so here, what it talks about on the far right side is the amount of potential nitrogen production. So at 12,000 protozoa, 12,000 flagellates, 10,000 amoebae that would be eating bacteria, you can produce approximately 100 to 150 units of nitrogen. The treatment, after 1 hour, we were at 10,000 and we hadn't stimulated our amoebae, just hadn't started yet. By 2 days, notice that the control had dropped back down because there was no stimulant in the water. The flagellates went from 12,000 down to just under 900. The amoebae went from 10,000 to 2,900. However, because of the stimulants and the minerals and availability in the soluplex for biorelease, our flagellates were at 17,000, our amoebae were at 29,000. And now we have that capacity of producing 100 to 150 units of nitrogen, where we're losing nitrogen potential with the microorganisms dropping down in the control. After 7 days, the control was back to where it was when it started. 12,000 flagellates, 12,000 amoebae. Ours, however, were at 590,000 flagellates. We were at 122,000 plus amoebae. Just with the amount of protozoa that could eat bacteria, we were over 300 pounds of nitrogen production per acre here. So this is a real crucial part of growing the right biology and having it in the system. And again, these fungi, we have soil biological tests that we can run, and we can find the active and total bacteria, the active and total fungi, the active or the protozoa groups, the nematode groups. And this begins to tell us what the health of a soil is. So if we look at fungi here at the fungal group, let's move forward. And this soil food web analysis shows us that we have 41 active fungi, but we have total 2,400 fungi, but they're dormant. They're not doing anything out there. Only the ones that are active are producing CO2. We have a tremendous amount of bacteria, 3,800 per milliliter, and we have only 67 active. So something is suppressing the active microorganisms in relation to the total. The total are hibernating. They're not functional. They're there, but they're not functioning. We look down here at our protozoa groups, and we'll come back to this one because we'll check it, and then we have a nematode reading below. And so we have active fungi at 41. We have total nematode at 1.2. So I've developed a calculator that we can put these numbers in, and it helps us get a feel for what nutrient cycling is possible and what activity is going on in the soil. And again, we go back to microbial cycling, protozoa eating bacteria releasing what they don't need, nematode eating fungi releasing what they don't need for their ratios. And we've already gone through this, so let's go into when we have very little active fungi, active bacteria, we have very little nitrogen production, 25 to 50 pounds of nitrogen being produced here. And so when you look at the scale, our row crops, what we grow, need to be 1-to-1 for 1 bacteria to 1 fungi. And the ratios need to be the same. Active bacteria to active fungi 1-to-1. Total bacteria, total fungi 1-to-1. So if I have total bacteria of 3,800, I should have total fungi of 3,800, but I don't. I have 2,400. And what I have here is active bacteria is 68. And at this point in time, it should have been a minimum of 970. So I can tell that that soil is not functioning at all. My active bacteria was 41. It should have been 970. So this one is not functioning. You go back to your mycorrhizal colonization, it was 13%. It should have been a minimum of 40 up to 80%. So that system is not connected. My nematode was 1.2. It should be a minimum of 20 to 30. So those aren't there as well. So there's no nutrient cycling happening here. You look at your protozoa groups, I've got 3,200 flagellates, 3,200 amoebae. And what I should have is 10,000 minimum of both flagellates and amoebae, and I have 3,200. So that system is not adequately cycling nitrogen, phosphorus, potassium in a plant. And so it's low mineral production. This is a biological soybean field that we took pictures of almost 15, 16 years ago in Minnesota. This is a side of the field that had biological stimulants. And this is what the plants are telling us. This gentleman is named Kevin Officer. He stands here in the transition zone between the biological side and the chemical side. And this is the fertilizer side of the field. Planted the same time, all the pictures were taken the same day. You can see the plant response. This is a biological corn plant with 6 ears.